It's a pretty common situation to want to know about rates of change with respect to time, even when you don't know any of the functions with respect to time. But there's still some tricks that you can pull to find rates that you want, even when you don't know the functions. This is the sort of situation I'm talking about. So suppose that 3 seconds into an animation, a circle in the animation is growing at 1/2 a centimeter per second, and at this very moment, how fast is the area of the circle changing? So in this situation, we have a circle. I should say what about the circle is growing. What I meant is the radius. So we have the radius of the circle. It's a function of time, right? So we should write r of t, but we don't know what this function is. We know this rate of change, 1/2 centimeter per second. So this is the rate of change of the radius with respect to time, but this is the rate of change only at this instant. So this is not the full function dr dt, it's actually the function at t equals 3. And then the other quantity in this situation is the area of the circle. So the area of the circle, since the circle is changing in size, its area is also a function of time. And we want to know how fast this area is changing, so I guess what we're really looking for is dA dt at this particular moment. So this is where we want to find dA dt at the moment when t is equal to 3 seconds. So you can see there are these functions that we don't know what they are, and we have no hope of finding what they are. We just don't have enough information. So it might seem that things look kind of bleak, but in fact, we do have enough information to find this rate of change, dA dt, at the moment in time when t is 3. And here's how we can do it. So these quantities, the radius and the area, they're related. We can write an equation that relates these quantities. Area of a circle is pi r squared. Right? Now, really, a and r, these are both functions of t. So we kind of have to keep in mind that they're functions of t, even though I'm not explicitly writing down the fact that they're functions of t, or I'm not reflecting that fact in my notation. Right? I'm not writing a of t. But we have to just keep in mind that they are functions of time, even though I'm not writing that. Now that we have this equation written down, well, we need to use this information somehow, this information we know about dr dt, and also we need to make dA dt show up somehow so that we can find it. So clearly how we should do that is just differentiate both sides. With respect to, well, t is the derivative we want to show up, so we'd better have a derivative with respect to t. All right, now on the left-hand side, the derivative with respect to t of a, remember a is a function of t, so the derivative of a with respect to t, that's dA dt. Now on the right-hand side, well, there's a product, right? This pi is a constant multiple rule, a constant multiple, so we can use the constant multiple rule and move it outside the derivative. And to calculate the derivative of r squared with respect to t, well, we have to be careful because r is a function of t, so this square function has another function inside of it. So we have to use the chain rule. So dA dt is pi times, so take the derivative of the outside function, the squaring function. The derivative of that is 2 times the inside squared, or the inside to the first power, but the inside is r. Now the chain rule says we have to multiply by the derivative of r. So that's the derivative of r with respect to t. So by taking the derivative with respect to time on both sides, we turned our equation relating a and r into an equation that relates the rates of change of a and r. So that's why this particular trick gets called related rates. Because when you differentiate an equation of functions of time, you get an equation that relates the rates of those functions. All right, well, still we can't use this information that we have, and we don't have this dA dt at 3 showing up yet because they just aren't evaluated at 3. So what we can do is actually evaluate both sides, right? Both sides of this equation are functions of t. So if these two things are equal, then when we evaluate them at 3, they're still equal. So we're going to evaluate r at 3, and then evaluate this derivative at 3. Okay, so I see now I left something out of part of my problem setup. I didn't say what the radius was at this particular time. So let's say that r, so I'm adding something to the problem now. Let's say that r of 3 is 5. Okay. Now this derivative, the derivative of a with respect to t at t equals 3, that's what we want to find. So it's okay that we don't know this yet. On the right-hand side, well, now we can use all the information we know. Pi is pi, 2 is 2. R of 3, that's 5 centimeters. And dr dt at t equals 3, that's 1/2 centimeter per second. I think I said a half. Is that a half? Yes. All right, and now we can put this all together. So the 2's cancel. We get 5 pi centimeters. Notice that the units work out. We get centimeters times centimeters, so centimeters squared per second. And this is a rate of change of area because centimeters squared measures area. So at time 3, the rate of change of area is 5 pi centimeters squared per second. All right, so the broad picture of what we did here was we wrote down an equation that relates the variables. We took derivatives on both sides with respect to time to get an equation that relates the rates, and careful about using the chain rule when we calculated those derivatives. When we have an equation that relates with the rates, then we plugged in everything we knew and solved for the thing we didn't know. Let's look at another example. So suppose we're filling this tank of water with 10 cubic feet per minute of water. When the water is 4 feet deep, how fast is the depth of the water changing? So this 5 feet, I mean the 5 feet to be the distance across this. The top of this thing is a square, and 5 feet is the length of the side of the square. And the 8 feet, that's from the very top to the very bottom, like this. Okay. Well, you can imagine that when we filled it part way, we're going to get the surface of the water at some height. And let's call that height h. Now h is a function of t, right? Almost everything is a function of t. The size of the tank is constant, but the amount of water in the tank down here is changing with respect to time, and so this height is also changing. I guess we could also maybe name the length of the side of this square that is at the level of the water. Maybe we could call that h, or x. And I guess another quantity in this problem that is going to be important is, we're adding water at a rate of 10 cubic feet per minute. So what is this the rate of change of? So it's 10 cubic feet per minute. So this is some derivative with respect to time. Well, it must be the derivative of something measured in cubic feet, but that's going to be volume. So we should also think about volume, V. The volume of what? Well, 10 cubic feet per minute, that's the rate of change of the amount of water in the tank. So this bottom part that's underwater, this volume is how much water is in the tank. So the quantities we have in this situation are the volume of water in the tank, the width of the top of the surface of the water here, and the height that the water reaches. And all of these are functions of t. They should all be related somehow. Remember, the first thing we want to do is, once we know what all of our quantities are, we should relate them all. Well, the shape that the water is taking down here is a pyramid, a square-based pyramid. And there's a nice volume formula for a square-based pyramid. It's 1/3 the height times the square of the length of the base, like that. All right, remember that v, h, and x, those are all functions of t. So we're going to take a derivative, but we need to be careful about the chain rule. So on the left, there's nothing to worry about. It's just dv dt. On the right, we can move this 1/3 outside of our derivative. Now to calculate this remaining derivative, this is a product, so we're going to have to use the product rule. So dv dt equals 1/3 times, now we have to do the product rule, derivative of the first piece. The first piece is h, and the derivative of that isn't 1. Remember, we're differentiating with respect to t. So the derivative of h with respect to t is dh dt, times the second piece with no derivative, x squared, plus h with no derivative, times the derivative of x squared with respect to t. But since we're differentiating with respect to t, right, this has an inside and an outside, so we have to do the chain rule. So derivative of the outside is like this, plug x inside of there, and then multiply by the rate of change of x. All right. So at this point, we have a relationship between all of these rates of change. So now let's try plugging in everything we know. So at this particular instant in time, we know dv dt, it's 10 cubic feet per minute. So I won't keep track of the units, but if you do keep track of the units, they all work out. In fact, let me quickly do that. So dv dt, that's going to be in cubic feet per minute. Over here, dh dt, h is a length, so that's going to be in feet. Dt, that's per minute. And then x is in feet, so when you square x, you get something in square feet. Okay, plus, so h is in feet, x is in feet, and then dx dt is in feet per minute. And so you can see the units are compatible. Here we have cubic feet per minute, this is cubic feet per minute, and this is also cubic feet per minute. So the units make sense. Okay, so now we can plug in what we know. dv dt, that's 10 cubic feet per minute, equals 1/3 dh dt. Well, dh dt is what we're trying to find, right? That's how fast the depth of the water is changing. So we don't know dh dt, but that's okay. That's what we're trying to find. What about x? Well, we don't know x. And, all right, there's nothing in this that tells us x. We know what h is. At the moment in time we care about, we know that h is 4. But if you think about filling up a tank, if you know that if you know the depth of the water in the tank is 4 feet, that should determine how wide the surface of the water is. So the shape of the tank should give us an extra relationship between x and h, and we haven't used that yet. So what is the relationship between x and h? Well, if you look at the side view of this tank, what we get is it's a triangle like this, and then the water makes a smaller triangle like that. But these triangles are these are similar triangles, right? They have all the same angles. It's just that the blue one is smaller. And on the small triangle, the dimensions we have are h and x, and on the big triangle, the dimensions are the dimension of the tank. That's 8 and 5. So similar triangles says that ratios of corresponding sides are equals. So if we do height divided by length for the big triangle, that's 8/5, that has to be the same thing as the height divided by the length for the small triangle, so h/x. Now we can use this equation in two ways. Well, first of all, why don't we clear this denominator on the right? So this says that h is 8/5x. So on the one hand, we can use this to find x. We know that h, at the moment in time we care about, h is 4. So 4 equals 8 over 5x. And then we can solve this for x. So this tells us that x is, I guess it's going to be 5 halves. So now we know x. It's 5 halves squared plus h is 4 times 2 times x, which we said is 5 halves, times dx dt. Well, right, nothing about this tells us dx dt. But if we look at this equation, if we differentiate both sides, we get dh dt equals 8 over 5 dx dt. So we can solve this for dx dt. Dx dt is 5 over 8 times dh dt. So we can put that in here. So times 5 over 8 dh dt. And you see that has the effect of replacing this derivative that we knew nothing about with the derivative that we were trying to find. So it's okay to have dh dt here. The resulting equation, dh dt, is the only unknown, so now we can solve for dh dt. So let's simplify the right-hand side. Actually, let's multiply both sides by 3 just to get that 1/3 out of the way. So we get 30 equals, and on the right-hand side here's 25 over 4 plus, let's see, these cancel, and these leave a 2 down here, so 25 over 2. And both of these have a factor of dh, so factor out that dh dt. And now we can do the fraction arithmetic here. So this is 30 equals, looks like it's going to be 75 over 4 dh dt. And then we can divide to get dh dt. So dh dt is 30 times 4 over 75. So let's see, 30 is 5 times 2 times 3. So get rid of a factor of 5, 15. And then get rid of a factor of 3. So 2 times 4 is 8 over 5. And since, right, we checked the units, so we know the units are correct. Since this is dh dt, this must be in feet per minute. All right. So this used the same idea as the previous example. Once we identified all of the quantities in our problem, h, x, and v, we wrote down relationships between them. So the obvious one was the volume relationship, but we also used this similar triangles relationship. Then we differentiated these equations. Turns out we had to differentiate both of them. Then we plugged in everything we knew, and we got an equation with just the single unknown rate of change that we could then solve for.